I'm back with the second section for today, and that's section 10.4, pressure, volume, and temperature. We just got done talking about pressure and gases, and that pressure is exerted because those gases are flying around really fast, and so they're hitting the surface and they're exerting a force on the surface, providing for that pressure. So now we're going to talk about how pressure, volume, and temperature are related, and this will lead into really the rest of the chapter. So we're going to take a quick look at these relationships, and then we're going to break them down and talk about them more in depth the rest of the chapter. So I'd like you to copy down this chart that I made. So I'll give you a few seconds to turn off the video and do that. Okay, so the first relationship here that I want to talk about, and I'm going to do one of these just to cover this up so we're focused, is I want to talk about just pressure and volume. We're going to keep temperature constant. So if we just talk about pressure and volume, and this really relates to a syringe. If you have a syringe that you can experiment with a little bit, that would help to see this relationship. And the relationship with a syringe is that if you increase the pressure on it, so if you push the plunger down, you decrease the volume. And this is usually, we would say with this, that you would hold like your finger over the end of the plunger so that you could also feel that, because we could also say that if you decrease the volume, you increase the pressure, and you can really feel that pressure on the syringe if you hold your finger over the opening on the other end and push that plunger down. Now, we also can tell that if we decrease the pressure, so if we let up on the syringe, it will increase the volume. That syringe will pop back up. And vice versa. If we were to increase the volume, we let off on the pressure. And so this relationship is what we call an inverse relationship. When we increase one thing and the other decreases, that's why I have the up arrow and the down arrow, so increase, decrease. When they're opposites like that, we call that an inverse relationship. Now let's take a look at another scenario. So let's talk about hot air balloons. Now hot air balloons, you know that they lift off by changing the temperature. The pressure is constant because we're talking about atmospheric pressure, so the atmospheric pressure is not going to be changing much while you're flying your hot air balloon. And what does change is the volume. So if we increase the temperature, we're increasing the volume of the air. That's why when you heat up the air for a hot air balloon, it fills up the balloon because that gas is expanding. It is filling up that volume of the balloon. So if you want to go up, you increase the temperature, it expands the volume, it lowers the density of the balloon so the balloon can go up. Let's say you want to come down. What you do is you turn off the gas, you decrease the temperature, the volume decreases, and that hot air balloon will come down because the density is lowered. So that's the second type of relationship. The third type of relationship has to do with your car tires. With car tires, you may notice that in the winter you have to put some extra air in them. And then in the summer, they don't need as much air. This is due to this third relationship. If we keep the volume constant, the size of the tube that we fill with air in our car tires, and we increase the temperature, it will increase the pressure of the gas. The reason for this, and I should have talked about this with the hot air balloon too, If you increase the temperature, those particles are flying around faster, and so they're hitting with more force, and that will increase the pressure. Likewise, if we increase the temperature up here, they're flying around faster, they will go farther and increase the volume. And down here, so that's in the summer, we increase the temperature, we increase the pressure. In the winter, we cool off those tires. The pressure decreases because they're not moving around as fast. And so they slow down and they're not hitting with as much force with the pressure. Now I have off to the side here with the hot air balloon and the car tires, notice increase, increase, decrease, decrease, increase, increase, decrease, decrease. When both quantities go up or both quantities go down, we call that a direct relationship. So for pressure and volume, they have an inverse relationship. For pressure and temperature and volume, they have a direct relationship. Now I want you to take a look at page 249, 8 and 9. Try to answer those on your own. So I'll give you a few seconds to turn off your video and take a look at those, and I will be back with the answers. Okay, so here are my answers. And I will explain these. Oh, the sun is really shifting here in my room and causing lots of problems with my video here at the moment. Okay, so on page 249, number 8, it says, what will happen to the volume of a gas in a closed container if you increase the external pressure when the temperature remains constant? Looking at my chart up above, if I increase the pressure but keep the temperature constant, I put this line here just to show that it's not changing. What will happen, according to my chart, is that the volume will decrease. Increase the pressure, the volume will decrease. This is like my syringe. For number 9, explain why a balloon becomes smaller when placed in a freezer. Well, this is like our hot air balloon. When pressure is constant and temperature decreases, volume decreases. I'm sure you've probably also had the experience with maybe balloons that you bought for a birthday party and you took them outside on a really cold day and all of a sudden they just really shrink up. Okay, that's the same idea. That you decrease the temperature so the volume decreases because those molecules of gas are really slowing down. Okay, so what I want you to do now is take a look at the homework on page 271, number 14, and do that homework. I'm just going to add those answers to those questions onto this video here, so that I don't have another video because it's really not running that long. So go ahead and pause and do your homework and then come back. Okay, so here is part of the answer to number 14. Here's more of the answer. And here is the last part of the answer. And what I'm going to do is I'm going to go through how to do all of those step by step. So you're filling in the chart, and on the chart for 14, my first quantities say that 44.5 psi equals 2.30 times 10 to the third torr. and they want me to find atmospheres and kilopascals. So I take my 44.5 psi. That's just, you could use the Torr. I'm not going to show that one. I'm just taking my first value, partly because it's a smaller number to write, and so I don't want to do more writing than I have to. And I know that 14.7 psi is equal to 1 atmosphere. This is from that list that we wrote out, okay? So I cross out my PSI. That list, I can't find mine right now, or I'd show you again. But it's the first, that list that we wrote in our notes. So when I do the division, 44.5 divided by 14.7, I get a value of 3.03 atmospheres. Okay, we're gonna do this again, 44.5 psi. But this time I'm going to convert that to kilopascals. So I know that 14.7 psi is equivalent to 101.3 kilopascals. PSIs cancel out, do the multiplication across the top, divide it by what's on the bottom, and I get 307 kilopascals. So that's the first row. For the second row, they tell me that 500 atmospheres, 500.0, equals 50,650 kilopascals. Could you turn on the light and see if it will even out some of this light problem I'm having, honey?
520 something gigawatts?
Yeah. Okay. My husband thinks he's funny. Oh, that didn't help. Go ahead and turn it off. Thanks anyway. Okay. So 500 atmospheres. I know that 1 atmosphere is equal to, now for this one I'm converting to PSI and Torr, is equal to 14.7 PSI. That cancels, so doing the multiplication across the top, I end up with 7,350 PSI. Now, I have to be careful with PSI. All the other values are really absolute numbers. They're pure numbers, but PSI is not. It is a measured number, and so I have to stick with my 3 significant digits for this number because PSI is the only one I have to worry about. And so I write my number like this. My 0 is not significant because there's no decimal point after it. So 500 atmospheres again. I'm converting to Torr this time. So 1 atmosphere is 760 Torr. Multiply across the top. I'm going to change this to scientific notation. So it's 3.800 times 10 to the 5th Torr. And this, because it's an absolute number, I don't go with that. I go with these. This number for the 4 significant digits. That's why I end up with this as an answer. Okay, so my next problem is 32.0 PSI. They want me to find atmospheres, torrs, and kilopascals. So 32.0 PSI. The first one I'm going to do is atmospheres, so 14.7 PSI is 1 atmosphere. Divide 32 by 14.7 and I get 2.18 atmospheres. Now what this means is that 1 atmosphere is basically the pressure we're used to. This is 2 times the pressure that we're used to here on Earth, is what that would mean. Okay, start with my 32 psi. And this time I want to convert to torr, so 14.7 psi is 760 torr. Multiply across the top, divide by what is on the bottom, and I get 1,660 torr. 3 significant digits, no decimal place, so I'm good because that 0 is not significant. Oh, sorry if you can't see that, and my light is really shifting here. The sun is really moving. .32 psi. I'm now converting to kilopascals, so 14.7 psi on the bottom, 101.3 kilopascals. Multiply across the top, divide by what's on the bottom, and I get 221 kilopascals. Okay, 1 set of conversions left. And I'm gonna adjust my camera, I guess, down here. Okay, for the last set, they give me 14.7 torr equals 1.960 kilopascals. I want to convert to atmospheres and psi. So 14.7 torr. I'm going to do atmospheres first. That's 760 torr are equal to 1 atmosphere. When I divide 14.7 by 760, I get 0.0193 atmospheres. So very little pressure there. Very little pressure. And my last one, 14.7 torr. 760 torr is 14.7 psi. Multiply across the top, divide by the bottom. 0.284 psi is my answer. So I will be back tomorrow, and we're actually going to go into more depth about that last chart we talked about with the pressures, the volumes, and the temperatures. So I'll be back.